Hi everyone, this is Delbert speaking, and in this part of this course we will analyze the results um, in terms of the metrics used to decide which is the best model. We have presented two different models, the multiplicative and the additive models, and visually they are quite similar, and to decide which is the best we can use some metrics. And let's start with the mean absolute error. The mean absolute error is the average in absolute values of the difference between the model and the actual data. So we have an absolute value which express the difference on average between the model and the actual data. In my opinion, better than the mean absolute error is the mean absolute percentage error, which gives the same idea of the mean absolute error, but in terms of percentage. So we can see in terms of percentage how strong is the relationship between the model and the actual data. So if the mean absolute percentage error is close to 0, the model is good. If it's close to 100%, the model is not good. Okay? In terms of variation, we have the R-square, which is the coefficient of determination, and it can computed by the following. So taking into account any observation t, we can compute the difference between the actual value for a month t minus the average value for considering all months during the period of analysis, can be written by the difference between the actual value and the model plus and the value obtained by the model plus the value obtained by the model and the average value. So developing this expression, we can prove that this expression is true. And in this expression, we have the square of the difference between the actual data and the average. So here we have an idea about how the data changes around the average in terms of squares, because we are interested in absolute values, and it is equal to the variation between the difference between the model and the actual value, and the variation of the model and the average. I mean, how this model, the objective is to observe how this variation can be explained by this variation. So ideally, this value, this summation should be equal to 0. And then the variation of the data around the average would be explained by the variation of the data, the model around the same average. Okay? So SS tot are the sum of squares. SS res are the sum of squares of residues. And SS rig are, here is G, the sum of square of the regression. Okay? So the R square can be computed by the the by dividing the sum of square of the regression by the sum of the square, and as the sum of square of the regression is the sum of squares of square minus the sum of the residuals, we can obtain the R square by 1 minus SS res, which is the sum of the residuals and the sum of squares. So if the sum of residuals are close to 0, then the R square is close to 1, and it means that we have a good model in our hands. If the sum of residuals are greater than 0, then the R square is reduced, is lesser than 1, and then the model is not so good as we could imagine. So let's compute it for the additive model and for the multiplicative model and see which model is appropriate for our application. Let's go to the spreadsheet. So if you remember the last class, we observed that the additive model and the multiplicative model are quite similar. Here we have the results associated with the multiplicative model, and we can change by the additive model, and they are very similar. It's difficult to identify which is the best model for this application. So let's compute the metrics used for comparing models and see which is the best. So here we have the absolute error, which is the difference of the results, the result obtained by the model for the first month of our period of analysis, the month 1, and the difference between the result obtained by the model and the actual value. And then we have the results for all months. Here we have the average. So the average of the error is 1.73. So we don't know if this number is high or low because we don't have a reference. So the best way to evaluate the error would be, in my opinion, the mean absolute percentage error. So for the additive model, here we have the absolute percentage for each month, the error for each month, and then we can compute the average, and here we have the error, the average error of the model compared with the actual data. So for this case, we have 3.8% of error, which is low. I mean, the model is good if we analyze this metric. To analyze the R square, how the variation of the model explains the variation of the actual values, we can use the R square. And here we have the SS tot for each month. Here we have the residue associated with each month. And here we have the regression term for each month. And then we use this value to compute the R square for the additive model. Everything in gray here we are computing for the additive model. So for the additive model, we have 78.5%, which is good. It's a good result. Means that uh, we have almost 8% of the variation of the result of the data explained by the variation of the model, which is quite good. So for the multiplicative model, we have the mean absolute error 1.72, quite similar with the additive model. The mean absolute percentage error is 3.79%, lower than the additive model, but similar. And finally, the R square is 78.9%, which is quite similar with the additive model. So for this case, the multiplicative model seems better, but the results are similar. We can obtain this R square value by comparing the actual data with the, the results obtained by the model. Let me put it graphically here. Here we have the actual value, and here we have the values associated with the model. So if we compute here the trend line, if we compute the trend line and ask to show the R square, we have here the R square value, and which is quite similar with the R square that we have obtained, 78.5%, 78.5%. So you can easily obtain this value by using the trend component. Okay, so that's it. I hope you have enjoyed this course, and let's see how can we use this information to apply in our activity in October. So see you there.